So, hello. Again, Sandy Shigota for the Evolutionary Computing Class exercises at Faculty of Engineering Rijeka. Our last exercise was adding a couple of sensors, our graph, our position graph, our vision sensor, and our sensing nose to our BubbleRobot, which we have created even longer before. Today we are going to be adding some code to actually make the sensors functional and to actually make our robot move. So your first step is accessing this child script here. In case your BubbleRobot doesn't have this script, you can just go here, add associated. I need to go to something that doesn't have a script already added, so add associated child script non-threaded Lua. So we can open this and let's start with some programming. Okay, so the first thing we're going to program today is going to be our nose here, but we need to set some initial values. So the most important thing in our script that we have to add in the syscall unit is basic robot clicker. It's going to basically show us, that's going to allow us to grab the robot and its parts and use them in the script. So here you can type robot base, sim get object, and please note we need to add a slash to access our bubble robot, which obviously the name here depends on what you named the robot here. Then we're going to grab all the other elements of our tree here by creating a robot collection element, and we're going to fill that collection. Specifically, we're going to fill the robot collection by using this function called handle tree, which is going to access all elements of this tree, starting with our robot base. And we are not going to use any options. And that's our basic element. My suggestion: run the simulation, see if there is an error. It isn't, keep going. Okay, so this is the basic code that allows us to just grab what we need. Then we're going to add proximity sensor code, and in the syscall unit there's not a lot of code to add here. You just go distance segment simulation.add drawing object y. This is going to be a single line that we are going to use as an indicator of when our proximity sensor detects something. So we're going to add the drawing line strip, and we're just naming the position and to which object it belongs and the color of the line. Okay, that's all that we need to add to the initialization script, but we have something to add to the sensing script, actually quite a lot. So first, this is going to be part for our proximity sensor, and we're also going to add a part for the collision. Let's start with this, and we're going to create some local variables. The result variable and the distance data variable is what we need, but the function is also going to return this object pair variable, which we don't use in this example, and the function that's returning those is called check distance, and we're going to name it as distance between robot collection and all and we're going to name it as if result is greater than 0. Why are we using a 0? Because if we run this code here, so let me just show you. So we're going to add a text, just a local variable of text that states the distance to object is, and I'm going to use distance data with W7. This is just an ID that in this setup that we have made points towards the hour proximity sensor. I'm going to print that text. So what happens here? Once I print that, you can see that the distance is continuously 0.79. Let me try. That was the wrong object to move. Okay, so we have moved it. It was grabbing an object that existed, but we can see that now that it's pointing all the way into the distance and we don't see anything, we can just add a floating view. It seems I have accidentally deleted it. So we have a floating view. There's nothing in front of us. If we move this cuboid in the view, we're suddenly getting a real distance. So the 0 simply indicates that there is nothing in front of us, actually that the distance is infinite. Okay, so we can go back to my script here. I don't want to print it all the time, just if the result is greater than 0, so if the distance isn't infinite, or if that isn't a collision, let's print that. And in case there is a collision, I can get that with a bit of a different code. So similar to before, we have result and pair handles. Pair handles actually also to check which elements are colliding. We won't do that in this example. So we can check the collision between robot collection, something that's handled internally by CoppeliaSim, and all other objects. And if you remember from the previous examples, if the value of collision is greater than 0, if it's 1, we have an actual collision. So if it prints 0, it means everything is fine. If not, we're going to print collision, and we're going to change the color of our distance segment to previously added. Great. So let's try running the simulation again. I think I made an error somewhere. Okay, so in line 25. Yes, I have used the variable as result and wrote that as results here. Small errors. They happen all the time when you're programming something. Okay, so we have some object that it's detecting here, possibly the floor or something in the distance. So let's move it. Let's move the cuboid to it. Great. So it's actually detecting the cuboid at a certain distance, and if I moving cuboid. Once there is, it actually comes to this cone, is going to change the color because there is a potential of collision, and if there is an actual collision, we can see that it prints it. So I need to close this. We can see that we have collision happening. Okay, so that's our proximity sensor code, but we have some additional sensors. So let's do the graph sensor now. We're going to go back to our script here, and we are going to basically enable us to track the position of our robot and display it on the graph. Graph display position. So we're going to go here and just use graph xy, get object BubbleRobot graph, make sure it's named the same as it has as it's named in the graphical interface, and then we're going to measure the position by adding the graph string. Not measure the position, but display the position by adding the graph string to the graph we have just defined as object position x in meters. No additional options, and we're going to do the exact same thing with y, and finally we're going to define the variable that is going to allow us to draw the actual curve on the graph. So we're going to define it for graph xy. We're going to select which tab of the graph we are targeting. Okay, I have made a mistake here. I need to have a comma. I'm defining which objects. I'm defining that I have two objects, and I'm defining which objects they are. So obviously you can see how you could modify this to be 3D if you were, for example, using a drone or something. Okay, so we have added that curve, and that should be everything we need to add here. Okay, we don't get an error for graph, obviously. We aren't actually plotting anything yet. So, to plot something, we are going to go back to our sensing code and start getting the graph positions. So we're going to get position of the graph we have defined, and then we are going to set the values string value as targeting graph xy. We're going to define the object position x as position 1, so we're getting that value here in the graph. Our graph is a part of our robot, and we can do the same thing for our position epsilon here and here. So let's run the simulation now. We can see we have some slight movement just due to I apologize, just due to inaccuracies in the simulation itself. But if we select our BubbleRobot and we decide to move it around, we can see that movement is actually noted on the graph. Okay, great. So we have taken care of this, we have taken care of that. Now we have two additional things that we can do. I can show you how to modify the vision sensor, and I can show you how to actually program the robot to move around for us a bit. Let's start with the vision sensor because it's simpler, so we can add a new script to the vision sensor. I have already added it here, but if you haven't, go here, associate the child script, and then non-threaded Lua, just not with the customization, with an actual child script. Here we are going to add a new function. Let me just pull up my reference. So in addition to these 4 functions that I have explained in the previous classes, you can get some other ones that are defined between CoppeliaSim. In this case, we're going to be using this one. It's called vision, and it will handle a lot of stuff for us, so we don't have to code a lot. We're just going to give a name to the data that we are collecting from the camera, and we're using the built-in sim vision functionality to get certain values. So we have sensor image to work image, which is going to transform our sensor image that it collects to a shape that our processor can handle, and we're going to simply use in data handle as a point to reference our data. After that, we're going to apply something that already exists. Now we could manually access this data and see what happens with it. Maybe even include some processing with our own filters that we prepare. But for simplicity, we are just going to use something that's already built in, and that's edge detection and work image. So I'm going to do it in data as we have so far. I'm going to set the threshold to 0.2, and the final thing that vision. Okay. And the final thing that I need to do here is I need to transform the work image back to sensor image, so I can actually display it. If I want to display it, if I'm just using it for processing, I don't need to do this part. So what happens now? We're going to get an edge detected image here. So if we run this, we won't, because I have made an error. String vision sensor child script detection work image. I forgot the time actually in Lua, not in C or something. Apologies. Now we can apply this, and we can say that we have a value just detecting the edges of what's going on. We can increase the threshold significantly to basically get fewer edges. We can say that we are no longer detecting these ones here, and we can play around, but this is how to modify basically the stream that happens with our vision sensor, because vision sensors are these days probably the most popular ones in the when it comes to mobile robotics. Okay, so the final part of this exercise, I know it's been pretty lengthy compared to the previous ones, but in the end is actually controlling our robot here and moving it. Okay, so let's open our BubbleRobot script, and we're going to add a few elements to our syscall for the robot movement. So let's define a variable that we'll call speed for now, and let's grab some stuff that we need, like our left motor, which we'll get in the same way we got the other stuff in the simulation with get object, BubbleRob, left motor. We're going to do the same for the right motor, make sure the names of the motors are correct. And then we're going to also grab our mass sensor, just because we will need to directly reference it for some elements down the line. It's going to be a bit clearer why I'm using it this way. Okay, I think that's all that we need. No, I have another time. It was -1. Great. So that's all that we need to actually move our robot. So let's go to our Cisco actuation and define something. So I will read the value of our proximity sensor. Here's why I need to name it, because I'm not using it in the sensing function, I'm using it outside. And that's going to give me the distance according to our proximity sensor. Then if the result is greater than 0, as we did before, we are going to set a variable called back until time, which we have defined previously as the current simulation time increased by 10. And okay, so this is me just setting a certain variable. So what I'm going to do now is I'm going to take that variable that I have set, and I'm going to check it against the current simulation time after I have set the variable to do comparison. So if that time is lower, target velocity as left motor speed. So I'm going to set the joint target velocity, I'm going to set the speed of the left motor and the right motor to the speed that we actually want to reach, which we have set to 1 here for now. This is basically, you know, when we went here to the robot, to our joint of the robot, we went to this dynamic properties dialog and set the target velocity to 0 to make the robot stand still. We are just changing that value through program instead of through graphical interface. In case where that back until time is currently running, I'm going to just do the same thing, except this time I'm going to move the robot in a different direction with a slower speed and the different speeds of the individual wheels. If you were in class, I would ask you why we're using different speeds, because we have a differential drive, which means that if this wheel is spinning faster than this wheel, it's going to turn, the robot is going to turn. So that's what we're trying to achieve. We're trying to achieve that when this robot hits something, it starts moving backwards and slowly turning for a certain amount of time. Okay, so that should work. Unless I mess something up, let me run the simulation. Then expected reach back until time. Okay. Yeah. So that right here, if then else, and okay. That should work. Let's try it. And we have a robot moving backwards, okay. it seems I have mistakenly turned the wheels in a different direction when I was adding them. No foul, we can just modify the speeds now and move it backwards to achieve forward movement. Okay, so now it's moving forward, you can see it coming closer, and once it hits this, it's going to start moving back, turning and trying to avoid this. We see that this wasn't enough, so we can just change this to, let's say, have it move 15 seconds, and actually speed it up, or speed it up a bit to move it faster. Let's try it with just speeding up the backwards movement. Okay, there we go, and now we have moved almost 90 degrees in those 10 seconds because we have increased the speed. So this is all that we would generally need to control the robot. There's just one other element that I want to show you, and that is adding your own GUI elements to the simulation in case you want to control something while the robot is moving during the simulation. So I'm going to add adding UI elements simulation. I'm going to define this with just a bit of XML. If you're not familiar with XML, it's not that scary. We're simply going to open a tag called UI, give it a title, give it a title here by calling it object alias base. So we're going to get the name of our robot base variable, which is BubbleRob, and to that we're going to attach we simply attach the string speed, and I'm going to set some parameters to our closable, some parameters to our GUI. So I'm going to say it can be closed, it can be resized, and it can be specifically activated. And then we need to, I can do that. Okay, I'm used to a bit more advanced text editors. Okay, so we have that here, and I'm going to just do this to add a multi-line code to the string. So to this basic GUI that I have, I'm going to add something that's called, I'm going to actually, a good practice is to actually close the tag immediately. So here, UI here, okay. Then I'm going to add something that's called an age slider. Which will have a minimum value of 0, a maximum value of 100, and when we change the value of it, so we have a slider, we're going to click on it and move it. When that happens, I'm going to tell it to connect to something which is called a callback function, and I'm going to add that callback function next. So I'm going to call speed change callback, and this will, when a callback happens, when we actually change the speed to this, is going to do something in our code. Okay. It will probably be a bit clearer when I actually add the function. Then I'm going to just create an empty label just to have a bit of space in our GUI element that we are creating. you can technically skip this if you're doing this at home, but honestly, if you're one of our students, you have this code added and available at Merlin, so you probably aren't typing it by hand. Okay, so I think I have created the UI here correctly. So I mentioned that I need to do this speed change callback. No problem. I'm just going to add another function. This time I'm not using a built-in syscall function. I'm creating my own. Change callback, and I'm going to reference the UI variable. Just to here, let me define it immediately. I'm just going to say it's simulation UI, and I'm going to create a window according to this XML file. We can actually test this to make sure it works. I think it should work. Oh no, I have made an error in my XML somewhere. That's a bit of a pain. Let me just check it because I have it written down in the title. Sim get object alias speed closable false to activate false. Baseline minimum 0, maximum is 100. And change speed change callback. I think that's the problem. We don't have a speed change callback. So let's define it quickly. Speed change callback. Hopefully that's it. ID. Maybe you're seeing the error and screaming at me behind the screen. Let's do this for now. Don't worry about it. I'm going to actually fill that up with proper code. Here. Done. No. We still have the HTML parser. Why do we have an HTML parser? We have UI title. That's fine. Closable is false. Resizable is false. Activate is false. We are adding this page ledger for 0. Minimum 0, maximum 100 maximum on change speed change underscore callback. With an ID of 1 and a close tag. We have a label with this text. And without the comma here. I think that might be the error. There we go. And we created this, and it just speeds up the robot, and it's making it a bit too fast. Yeah, it doesn't. It screws with our robot a bit because we haven't finished writing the code, and it was simply too fast for the code to react at what was the speed I said 5. Yeah, so basically what happened was that when I called this, when I activated the slider, it called this function, it set the speed to 5. We don't want to set it to 5, we want to set it to something that makes sense. So to do that, I'm going to define the minimum and maximum speed as a variable min max speed, and it's going to contain two elements. This is the lower speed, which I'm going to define as 50 pi divided by 180, and the second is going to be 300 times math pi divided by 180. And I'm going to set the initial slider value. So I'm defining which slider I'm targeting. I'm targeting the slider from QY, the first one, and I'm just going to define the speed as 100 times the current speed, which is 1, minus the first element, so the lower the minimal speed, divided by the difference between the higher and the lower, so the minimal and the maximal speed, the range of speeds. Okay, and this is just going to set the original slider value. You can play around with this to modify the initial speed, and finally I'm going to change the actual speed based on the position of the slider that I select. So I'm going to set the variable speed to be the lower edge of the lower the minimum speed, plus the range of the possible range of values, so min max speed 2 and minus min max speed 1 times the new value we have obtained from the slider divided by 100, because we are multiplying it by 100 here. So let's see if that works. Okay, however, robot, let's see if we can increase its speed. We can, and the maximal speed here is a bit too fast for it. Let's try that again, just increase it slightly. Yeah, it still works. The problem is when we increase the speed way too much, the robot doesn't have time to react, and it crashes and panics. So obviously, to avoid that, we can modify the max speed that we can achieve in the code. That's something you can play around with, but for example I can set it to 200. So now that I run this at maximum speed, the robot will bump, but it's still not fast enough to actually it's not fast enough to actually crack. Something you can see, because we have used the speed as a modifier for our evasion, right? If we increase the speed, it's actually going to do a very large turn before stopping. So there are better ways of doing that, but I just wanted to demonstrate some basic principles of mobile robot programming in Lua within CoppeliaSim. So that should be it. So we have the vision sensor, we have our graph, we have our proximity sensor programmed, and we are controlling the robot based on these parameters. So thank you for your attention, and this concludes the second part of the exercises with our BubbleRobot. Hopefully you found it interesting, and I'll see you with the next set of exercises that are upcoming.